Separation of Flue Gas, an informative report by Joseph Middleman. The purpose of my report is to inform potential process engineers of the interfacial phenomena used in the separation of colloidal flue gas, especially those used in the processes at Trimble County Coal Plant. My paper will also include some EPA regulatory analysis, which isn't included in this presentation because the information has not yet been released. First, we'll start by defining what is a colloid. A colloid, as defined by LibreText, is a distribution of one material in another in which the particle size ranges from 1 nanometer to approximately 1,000 nanometers, or 1 micrometer. Below 1 nanometer, particle size is almost indistinguishable from homogeneous solution and is treated as such. That's why you'll see in Table 4.1 from page 119 in the Interfacial Engineering textbook that there are solid, liquid, and gas dispersions in the solid and liquid phases, but there's no gas dispersion in the gas phase. That's because it doesn't reach the minimum particle size to be defined as a colloid. As mentioned before, the site of study for my paper was the Trimble County Coal Plant. It's located approximately 50 miles northeast of Louisville on the Ohio River, and it houses 2 coal burning units, TC1 and 2, whose flue gas is examined in this report, as well as 6 gas burning units, TCs 5 through 10. Here you'll see some comparisons of the 2 units, TC1 and 2. On the left, you'll see some process specifications. On the right, you'll see some air emissions information. And in the middle chart, you'll garner that TC2 is the larger, newer, higher generating unit of the 2, as well as some of the air quality control systems that I'll be going over in this presentation. We'll start with a schematic of the air emissions flow for TC1. Flue gas is sent from the process through a selective catalytic reduction unit, followed by a hydrated lime injector unit, and then a dry electrostatic precipitator unit, followed by another hydrated lime injection unit, and then finally a flue gas desulfurization unit before being sent out the stacks. Here you'll see another flow chart for TC2 as well as an aerial view of the Trimble County Coal Plant. So flue gas enters a selective catalytic reduction unit, followed by a dry electrostatic precipitator unit, followed by a pulse jet fabric filter unit located in the FF bag house, followed by a flue gas desulfurization unit, and then finally a wet electrostatic precipitator before being sent out the stacks. We'll start with the selective catalytic reduction unit, which generally uses some type of reductant, either aqueous ammonia, anhydrous ammonia, or urea, to pull nitrous oxides from the flue gas. As you'll see from the schematic on the left, for an aqueous ammonia cycle, ammonia is vaporized, mixed with a air stream, and then mixed with the flue gas stream before being sent to a selective catalytic reduction unit. And in this, the stoichiometry provided proceeds, and nitrous oxides are pulled from the flue gas. Here you'll see a hydrated lime injection unit with the stoichiometry provided. A hydrated lime unit's main purpose is to react to some sort of sorbent, usually a limestone slurry, to pull sulfur dioxides and other sulfates out of the flue gas. A hydrated lime injection unit uses pulverized hydrated limestone calcium dihydroxide, which is mixed into a slurry and finally misted through nozzles over the flue gas, where the main byproducts pulled out are gypsum, calcium sulfate, and water. Next, you'll see a flue gas desulfurization unit, which works on the same principles as a hydrated lime injection unit, but it uses a different sorbent. Instead of a calcium dihydroxide, it will use a calcium carbonate or regular limestone slurry. This, once again, is finely misted over the flue gas, and it pulls out gypsum as well, calcium sulfate, and carbon dioxide as major products. Here you'll see a schematic of a dry electrostatic precipitator unit. A dry electrostatic precipitator is the base separation for the colloidal flue gas. It consists of tubes or plates connected to electrodes which supply a large voltage differential. This voltage differential causes these plates to be charged, and the charged particulate matter, the fly ash and dust, then coats these plates or tubes and builds up until it is sheared off using some type of wrapper, whether a sonic horn or a mechanical vibrating wrapper or a hammer strike wrapper. to cleave the dust and particulate matter into hoppers, where it is then repurposed or sluiced to a fly ash pond. Here you'll see the wet electrostatic precipitator unit. It works on the same basis for entrapment of the fly ash. It uses electrodes connected to tubes or plates. However, rather than using a wrapper system, it will use water streams to cleave dust and particulate matter from the plates before it is then sluiced or dried and repurposed, as with the dry electrostatic precipitator unit. The final system we'll see is the pulse jet fabric filter, which works on the basis of separating the particulate matter out of flue gas. As you'll see from the schematic on the left, it uses induced fans to pull the dirty gas through long tube-like bags with a very fine fabric. The gas is allowed to escape through the fabric, whereas the particulate matter builds up. To prevent clogging, compressed airlines occasionally shoot jets of air to blast particulate matter out of the bags, and it is then hoppered and dried, repurposed, or sluiced to a fly ash pond. In conclusion, the interfacial properties used in the system, in the dry and wet electrostatic precipitator units, the colloidal separation was achieved by use of the property of fly ash and other particulate matter being a charge. The wet and dry electrostatic precipitator plates use a voltage difference to entrap the charged particles, and this allows them to be separated out of the flue gas. In the sorbent reaction, the hydrated lime injection unit and the flue gas desulfurization units, the sorbent is finely misted over the flue gas, and this allows for maximum surface area for the droplets to collide with the flue gas in which the reaction occurs. Here are the sources used for the presentation, and I thank you for your time.